A municipal emergency management office builds a language model to help dispatchers query 15 years of storm event records. The model loads, the retrieval layer works, the interface is clean. On the first real day of use, a dispatcher asks about tornado activity in a specific county over the past 5 years. The model returns 3 events. The actual record contains 11. 8 events are missing because the source data used 3 different county name formats across 15 years of records, 2 abbreviations and 1 full name, and the ingestion pipeline treated them as 3 different counties. The model did not fail. The data failed. The model just made the failure invisible by answering confidently what it had. This is the article that prevents that scenario. This is Your Data is Not Ready. Models, Part 5. The model is the last thing you should worry about. The data that feeds it is the first. Section 1. Why language model make bad data worse. Traditional databases fail loudly. A query against malformed data returns an error or an empty result. The problem is visible immediately. Language models fail quietly. A model querying malformed data returns a confident, grammatically correct, well-structured response that happens to be wrong. There is no error message. There is no empty result. There is an answer that sounds authoritative and is missing 8 tornado events. This is the property of language models that makes data preparation more important here than almost any other system you will build. The model will not tell you the data is bad. It will use whatever it has and present the result as if it is complete. Section 2. What raw data actually looks like. The NOAA Storm Events database is public, well documented, and genuinely messy. That combination makes it the right through line for this arc. A clean synthetic data set would let you skip the problems. NOAA forces you to solve them. The database covers storm events across the United States from 1950 forward. Each record contains structured fields, event type, state, county, begin date, end date, injuries, deaths, property damage, and crop damage. Each record also contains a narrative field, a free text description of what happened written by the National Weather Service forecaster. The narrative field is where the language model value lives and where the data preparation work is hardest. The structured fields have their own problems. Property damage values are stored as strings with inconsistent magnitude suffixes. A record might show 10K or 10K or 10,000 for the same value. County names appear in multiple formats across different years. Event type classifications change over time. What was recorded as thunderstorm winds in 1990 might appear as thunderstorm wind in 2005. The date formats are inconsistent across decades of records. The narrative fields compound this. Forecaster writing style varies. Some narratives are 2 sentences, some are 12 paragraphs. Some reference external reports. Some contain abbreviations that mean nothing outside the National Weather Service. Some are missing entirely. This is not a pathological data set. This is what 15 years of generationally generated records looks like in any domain. Healthcare records look like this. Legal filings look like this. Financial disclosures look like this. And NOAA is the representative case, not the extreme one. Section 3. The 4 problems you will solve. Data preparation for each language model pipeline resolves into 4 distinct problems. Each one has to be solved before the next layer of the stack can do its job. First, normalization is the county name problem from the opening scenario. Inconsistent representations of the same entity have to be resolved into a single canonical form before ingestion. This applies to place names, event classifications, data formats, measurement units, and any other field where the same value appears in multiple formats across the dataset. A model that ingests unnormalized data learns that Jefferson County and Jefferson CO and Jefferson CTY are 3 different places. Every query about Jefferson County will return incomplete results. Second, cleaning is the removal of records that cannot be used. Missing narratives, corrupt fields, duplicate records, and entries that fall outside the scope of your use case all have to be identified and handled explicitly. Handled does not always mean deleted. A record with a missing narrative but complete structured fields may still be useful for certain query types. The decision has to be made deliberately rather than by default. Third, formatting is converting whatever structure the raw data arrives in into the structure the pipeline expects. NOAA data arrives as CSV files with 1 row per event. The pipeline needs those rows converted into documents that preserve the relationship between structured fields and narrative text. The document that presents the structured metadata and the narrative as a coherent unit gives the embedding model more signal than a narrative stripped of its context. Fourth, chunking is the decision about how to divide documents for embedding and retrieval. This decision has more impact on retrieval quality than almost any other choice in the pipeline. A chunk that is too small loses context. A chunk that is too large dilutes relevance. For Noah storm narratives, a chunk that captures a complete event description with its associated metadata is more useful than a chunk that splits a narrative mid-sentence to hit a token limit. We covered chunking strategy in depth in the next article, when ingestion becomes practical rather than theoretical. Section 4. What language model ready actually means. A dataset is language model ready when 4 conditions are met. First, entities are consistent. The same place, person, organization, or concept is represented the same way everywhere it appears. Jefferson County is Jefferson County throughout. Second, documents are coherent. Each unit of text that enters the pipeline contains enough context to be useful on its own. A narrative stripped of its event date, location, and classification is harder to retrieve accurately and harder for the model to use correctly when retrieved. Third, coverage is understood. You know what is in the dataset and what is not. You know which years are complete, which event types are well represented, and what the gaps are. A model that does not know what it does not know will answer questions about gaps as confidently as it answers questions about well-covered areas. Fourth, provenance is intact. Every document in the pipeline can be traced back to its source record. When the model produces a response, you can identify which source document contributed to it. This is not an optional polish for regulated use cases. It is the mechanism that makes the system auditable and the response is trustworthy. Section 5. What comes next? The next article moves from diagnosis to execution. Data in hand, no records downloaded, the ingestion pipeline gets built. Cloud Code prompts cover the normalization, cleaning, formatting, and chunking decisions that this article named as problems. The pipeline that emerges from that article feeds every layer above it in the stack. The model is still several articles away. That is deliberate. Stack article established the sequence. This article established why the sequence starts here. The next article makes it executable.